Okay, now let us continue our discussion and derive some additional Fourier transforms of functions of time which are not once again absolutely integrable over a infinite range. Okay, but at the same time they are not periodic. Like the cases we have just now considered in one of the previous lecture. Okay, so that is the example that we consider is unit step function. U of t, right? If you plot u of t, it looks like this. The magnitude is 1 from t equals 0 onwards, and it is 0 up to this one. So u of t is equal to, let's say, 0 for t less than 0 and 1 for t greater than 0. At t equals 0, it is undefined actually. Sometimes people will say u of t is equal to, take the extreme limits, this value is 0 and this value is 1. That means what? U of 0 minus is 0 and u of 0 plus is 1. You take the average of this. So 0 plus 1 by 2 is equal to 1/2. That means exactly at u of 0 is equal to 1/2. So you can write the definition as 1/2 when t equals 0. So this is a typical definition of your unit step function. So let me write down properly. 0 for t less than 0 and 1/2 for t equals 0 and 1 for t greater than 0. Now we would like to find out the Fourier transform for this function. How do you find out? Let me say x of t is equal to u of t. So x of j omega is equal to integral of minus infinity to plus infinity x of t. Now we are going to not consider this guy. Okay, we are going to consider these two conditions, general conditions. E to the minus j omega t times dt. Now what is x of t? X of t is u of t and its value is 1 from 0 to infinity. E to the minus j omega t times dt. Now you can write this as cos omega t plus, is it plus or minus? Minus j times sin omega t multiplied by dt, and the limit is from 0 to infinity. And the formulas, again you can break this into two integrals, 0 to infinity cos omega t minus j times integral of sin omega t times dt, and the limit is 0 to infinity. Okay, we have derived the formula for this two integrals, this guy and this guy. 0 to infinity cos omega t times dt is pi times del of omega minus j times, this guy is going to be 1 by omega. Okay, so this is going to be pi times del of omega plus, if j goes to the down denominator, then it becomes plus 1 by j omega. So this is the Fourier transform of u of t. So u of t has Fourier transform pi times del of omega plus 1 over j omega. So this is the final result that we got now. This 1 by omega comes from this integration, and this pi times del of omega comes from this first integration. Now how do you plot for this guy? In fact, this is a complex quantity, right? It is a complex quantity. Therefore, it has both magnitude and phase. Let us plot the magnitude. So, if you plot the spectrum, there will be an impulse. That impulse is located at omega equals 0. So, what is the strength of the impulse? Pi. Okay. Now, you have 1 over omega. So, if you plot like this, it goes like this. When maybe I will write down. When omega equals 0, let us take this guy. Okay, this has 1 by omega. When omega equals 0, this is infinity. Therefore, it comes from infinity and exponentially decreasing like this. This is 1 over omega. And similarly, for negative frequency also, the same happens like this. This is 1 over omega, where in this case omega is negative and in this case omega is positive. It's a magnitude. If you take magnitude, then it is a symmetric function. And there is a delta function, and the delta function is amplitude strength is pi. Okay, so this will be the magnitude of Fourier transform of u of t. Okay, so you have a continuous spectrum of decreasing amplitude, this one, as omega increases and corresponding to 1 over omega. Okay, because if you take a function like this u of t, this u of t is neither even nor odd. Therefore, we cannot expect the Fourier transform to be either purely real or purely imaginary. And indeed, it has got a real component, it is here, and imaginary component 1 over j omega. So, therefore, it is a complex quantity. Okay. So, we know that unit step function is obtained by okay, let us say your u of t has Fourier transform pi times del of omega plus 1 over j times omega. Now, we can look at is there any other way to derive this formula in an alternate way. Let us try. Okay. So, how we can sort of justify this result through some other means, some other method. We know that a unit step function is obtained by integrating a delta function, right. So, if you have a delta function, this del of t, then if you integrate your del of tau d tau and minus infinity to e, then this is going to be what? Your unit step function u of t. Okay. Or in other words, you can say your unit step function is the derivative of the unit step function. And since we know the rule for the derivative of f of t, please recall from one of the previous lecture, and how it gets transformed in the transform domain. Okay. So, recall the property of derivative, differentiation, the time domain. X of t has Fourier transform x of j omega, then d over t of x of t has Fourier transform j omega times x of j omega, right. Now, what is del of t? Del of t is d by dt of u of t. That means what? Fourier transform of del of t is equal to Fourier transform of d by dt of u of t. Now, if you take Fourier transform of d by dt, then it becomes the d by dt will go away by simply multiplying j omega and then Fourier transform of u of t. Okay. So, in the left hand side, the Fourier transform of del of t is 1. In the right hand side, it is j omega. So, if you rearrange this, 1 over j omega is equal to Fourier transform of u of t. So, Fourier transform of u of t is equal to 1 over j omega. But just now we found the Fourier transform of u of t is equal to pi times del of omega plus 1 over j omega. Now these two are contradicting results. They are not, let me call this is 1, okay, 2 and this is 1. Why? Just now we have derived this. Where is it? Yeah, this is what we got now. U of t is equal to pi times del of omega plus 1 over j omega. But using your differentiation property, you got something completely different result. So in that case, what shall we do? Okay, so the Fourier transform of u of t is 1 over j omega using your differentiation property. And here using some ambulance sound. It is really painful to record. So much disturbance. Okay, anyway, what to do? Correct. Okay, now equation 2 is different from equation 1. Okay, from equation 1 it says this Fourier transform is obtained using your Fourier transform formula, and this one we got through differentiation property. So there is something, no mistake in equation 2, so in differentiation property. Okay, so equation 2 is not in accordance with what we have derived using Fourier transform formula. So we need to find out what was the problem. So obviously there is something, inconsistency here. Okay, so the steps here, like this is the correct formula. Del of t is equal to derivative of u of t, and then you take Fourier transform on left hand side as well as on the right hand side. Del of t is 1, and the right hand side this d by dt becomes j omega, and again Fourier transform of u of t. So this j omega you brought to the left hand side, so 1 over j omega is equal to Fourier transform of u of t. Okay, so it seems that these steps are in order, but there is some small mistake. Okay, what is that mistake? What is the catch here? The catch here is whenever you are dividing by j omega. Okay, so you have some Fourier transform x of j omega or y of j omega. Then if you divide by j omega, something like this. So whenever you divide some quantity by j omega, then you must also take possibility of a delta function being present. Okay, so in fact what you have to do is j omega times 1 over j omega plus k times del of omega. Like this you should take it. In the left hand side, what do you have? The left hand side you have 1, right? In the right hand side you have Fourier transform of j omega times Fourier transform of u of t. That's what we have. This one I can write as j omega times 1 over j omega plus k times del of omega. How can I justify this? Because you multiply this guy inside, then j omega cancels, then 1 plus j omega times k times del of omega. Now what is this guy? We know the property from your delta function. X of t multiplied by del of t is equal to x of 0 times del of t. Similarly, x of omega, let's say x of omega, j omega, multiply by del of omega is equal to x of j times 0 times del of omega. So recall this property. Therefore, what will happen? You substitute wherever you find omega, there you substitute omega equals 0. Therefore, 1 plus j times 0 times k times del of omega. So 0 times anything 0. So this is 1 plus 0, which is 1. So the same one we got here. Okay. So therefore, whenever you have some Fourier transform, and the transform you are about to you wanted to divide by j omega, then there is a possibility of a delta function. So we should add that. Okay. So whenever a function x of j omega is multiplied by del of omega, then that x of omega can be replaced by x of j0 times del of omega. Please recall this property, remember this. Okay. After all, this is a delta function and has a value only at omega equals 0. That's why you are putting omega equals 0 here. Okay. Therefore, of course, this Fourier transform of u of t is equal to 1 over j omega. Of course, this is true, but it is not a general expression. Okay. This is correct, but not completely correct, but not, it is a general expression. Okay. So therefore, this Fourier transform of u of t, this general expression is whenever you are dividing by j omega. See, initially you had j omega times Fourier transform u of t, which is equal to 1 in the right hand side. Now what I am saying is, you replace this 1 by what you do is j omega times 1 over j omega plus k times del of omega. Okay. So now this we already proved, this 1 can be written like this. Okay. Now bring this j omega to the right hand side, then Fourier transform of u of t is equal to Fourier transform of u of t is equal to j omega divided by j omega times 1 over j omega plus k times del of omega. Please remember how I got this step. This 1 can be written like this. This just now we justified. Look at here. So whenever you have 1, that 1 can be replaced by this quantity, because again this is 1. You multiply this inside, then j omega times 1 over j omega 1, then j omega times k of del of omega, j omega times k times del of omega. By impulse function which is multiplied by some function, then it has value only at omega equal to 0. So 0 times anything 0. So finally again you got 1. So whenever you have 1, that 1 I can write like this in the transform domain. So that's what I got it here. Okay. So this one is replaced by like this. And then you bring down this j omega to the right hand side to the denominator. So this j omega and that j omega will get cancelled. Therefore, your Fourier transform of u of t is equal to 1 over j omega plus k times del of omega. Okay. Now, what is the value of k? That is the next question that one should ask. K is equal to what? How do we get the value of k? In the earlier derivation, we saw that using Fourier transform formula, this is equal to 1 over j omega plus pi times del of omega. Therefore, the k value is going to be pi. Okay, now now what you do is, let me denote this one as x of j omega. What is x of j omega? 1 over j omega plus k times del of omega, and we don't know what is the k value. Now we need to find out the k value. So how do you find out? One method is you find the inverse formula for this. What is the inverse formula? Inverse Fourier transform. If you take inverse Fourier transform, you will get u of t, right? Because after all, this x of j omega is what? Fourier transform of u of t. That's what we got from there. Now if you take inverse Fourier transform, then you get back u of t. So what is the inverse Fourier transform formula? Your Fourier integral 1 over 2 pi integral of minus infinity to plus infinity x of j omega times e to the j omega t times d omega. So 1 over 2 pi integral of, what is x of j omega? It is here 1 over j omega plus k times del of omega. So 1 over j omega plus k times del of omega multiplied by e to the j omega t and d omega. So this is my u of t. Now let me substitute a value of 0 for t. Why? Because I need to find out the constant. Somehow I need to simplify this integration and find the value of k. My goal is not to find the inverse Fourier transform. My goal is to find the value of k. What is the value of k? Somehow, some brilliant way you can find the value of k. So what I will do now is, you put t equals 0 in this one. So u of 0. U of 0 is equal to 1 over 2 pi integral of 1 over j omega plus k times del of omega. This is multiplied by e to the 0, that is 1, times d omega. Okay. Now you observe this expression very carefully in the right hand side. You have two integrations, 1 over 2 pi integral of minus infinity to plus infinity 1 over j omega times d omega plus 1 over 2 pi integral of minus infinity to plus infinity k times del of omega times d omega. In the left hand side you have u of 0. Now what is this guy? This guy is an odd function, right? Omega is 1 by j omega is an odd function. Odd function. So if it is odd, then the limit is symmetrical. That means we are integrating between symmetrical limits from minus infinity to plus infinity. Then this first integral leads to 0 value. Okay. The positive area and the negative area cancel themselves out. So the first integration is 0 plus the second integration is 1 over 2 pi, and again the k is constant, you can pull out from the integral d of omega and d omega, and again what is this? This is the area under impulse function. So what is the area? This area is equal to 1. Therefore k divided by 2 pi in the right hand side. What is the left hand side? U of 0. Now the question arises, what is the u of 0 value? We said u of 0 is equal to 1/2. In the beginning of the lecture we said 1/2 because your unit step function is like this. So u of t is equal to 0 for t less than 0, and u of t is equal to 1 for t greater than 0, and u of t equals 1/2 when t equals 0, exactly t equals 0. How do you get? You take the two extreme points, this is 0 and this one is 1, take the average of that. So 1 plus 0 is 1/2. 1 plus 0 by 2 is equal to 1/2. Therefore this u of 0 is going to be 1/2 is equal to k by 2 pi, and this 2 will get cancelled. Therefore k is equal to pi. So the constant value is pi. Now in the above expression you substitute k is equal to pi. If you substitute k is equal to pi, then this is 1 over j omega times plus pi times del of omega. Now this result is inconsistent with the result which we derived using your Fourier transform formula. Okay. Now let us look at this u of t in another viewpoint. See, the Fourier transform of u of t can be derived like 2-3 ways. First way is using Fourier transform formula, and the second one is using the derivative of unit step function is an impulse function. Using that you can find out. That's what we have seen now. The another one is, what is u of t? U of t has a step function like this. It is 0, and then suddenly it jumps and it maintains 1, and this will be equal to, you have a constant function of amplitude 1/2, and then you have another function which I define like this. When t less than 0, when t is less than 0, its value is -1/2. When t greater than 0, its value is +1/2. Let us say this is x1 of t and then x2 of t. You add term by term now, point by point. Then what will happen? Let us say x of t is equal to u of t. Now up to this range it is -1/2, and here it is +1/2 plus 1/2. If I add these two things, then it will become what? It will become 0. Therefore up to this point it is 0. When t is greater than 0, in this range it is +1/2, and here also it is +1/2, +1/2 plus 1/2. Therefore the magnitude becomes 1 in the t greater than 0 range. When t less than 0, it is 0. Therefore your u of t can be thought of the summation of a constant signal 1/2 plus 1/2 and -1/2, where t greater than 0 and t less than 0 respectively. Now you can find out the Fourier transform of this guy very easily. What is a Fourier transform? If you take one Fourier transform, then 2 pi times del of omega. Instead of 1, I have a constant 1/2. If you take Fourier transform, then it becomes 1/2 times 2 pi del of omega. So this 2 will get cancelled. So the Fourier transform of this guy is pi times del of omega. Now what about this guy? If you take Fourier transform, we have already looked at this. This one has the Fourier transform of 1 over j omega. Okay, now add these two guys. Okay, this we already worked out in one of the previous lecture. Please go through this type of functions. I'm sorry, this one. Okay, so this function has the Fourier transform of 1 over j omega. Now add these two guys, then 1 over j omega plus pi times del of omega. Any other point I missed out in this? That's all. So therefore a unit step function can be resolved into two functions. One is pure DC. This one is pure DC. And another one, another which is an odd function. So they like this, an odd function which has a value 1/2 for positive t and -1/2 for negative t. So this is an odd function. So odd function has a Fourier transform purely imaginary. Recall this property. purely imaginary. And therefore the Fourier transform is purely imaginary, that is 1 over j omega. And this type of function, odd function, is important, okay, which appears again and again. So we will try to derive this, okay, in the next lecture. It is something called Signum function, okay. So we can see that a unit step function consists of partially a pure DC like this, and a function something called a Signum function. So let us discuss about the Signum function in the next lecture. Therefore, the Fourier transform of u of t can be derived by 2-3 methods. The first one is using Fourier transform formula, and the second one is derivative property, and the third one is you can think of u of t as summation of a DC signal plus a Signum function. So by using these 2-3 methods you can find out the Fourier transform. So let me stop at this point. In the next lecture we will discuss Signum function.